All right, we are on 19.7. We just went through looking at enthalpy, entropy, and the two combined, kind of culminating in this equation here, learning how enthalpy and entropy and temperature can affect whether a reaction is favorable or not. And we know whether a reaction is favorable or not by whether or not this is negative. Remember, negative delta G is a favorable, thermodynamically favorable reaction. It's called the Gibbs free energy, and it's a function of enthalpy, temperature, and entropy. Okay, we're going to take this one step further, and we're going to look at enthalpy, entropy, Gibbs free energy, and K. Remember, we looked at K. We knew that if K, the equilibrium constant, is greater than 1, the reaction is favored towards the product. So that is also an indication of how reactions will proceed. So let's take all of this and put it together. Now, here's a table. This is the Haber process, right, for the making of ammonia. And we've got some enthalpies of formation, some entropies. Notice that my entropies for all of the formation of these are all positive. But we're going to calculate delta H, delta S, and delta G. So I am going to go through this part of it pretty quick because this is just products minus reactants. If you don't get to copy this down, I'm leaving the units out, then you can come back and you can go back to the video and get it there. And this is equal to a negative 92.4 kilojoules, right? So that means that the formation of ammonia from these two products is an exothermic reaction. Then we have delta S, 2 times 192.5 minus 191.5, it's in parentheses, plus 3 times 130.6, and that is equal to, I'm going to pull this over here a little bit, negative 198.3. That makes sense, doesn't it? This negative value, because I'm going from 1, 2, 3, 4 particles to 2. They're all gases, but the quantities of particles is going down, so that is negative. Then I'm going to look at delta G, and that can be calculated negative 92.4 kilojoules, right? We're going to take these two, and we're going to use delta G is equal to delta H minus T delta S. So this would be a very typical FRQ problem where you would be expected to start from tables of these values to get to here. We're going to call this 498K times, remember, we've got to convert that to kilojoules. Don't forget that, or you will get the wrong answer. And that equals negative 33.3 kilojoules. So that means that this is a thermodynamically favored reaction. Now, if we want, however, we can also look at how delta G and K are related to each other because they each tell us a little bit about favorability. So on your formula chart, we'll start ticking them off. We've done this, we've done this, we've done this, and now we're going to look at that. So delta G is equal to a negative RT times the log of K, and that K is your equilibrium constant. R is a gas constant, and what you're going to do if you look at this, you're going to use, this is in joules, R is in joules per mole per K. So what does that mean? Again, I'm going to put this in red. We are going to have to manage our constant. This value needs to be converted also into kilojoules. We've got a temperature and we've got a K. All right, so if I've got delta G now, I can calculate my equilibrium constant. And that's always favorable information. We've done that many different ways before. So that's what we're going to do next, is equal to negative RT times log of K. Now, what I'm going to do here is I am going to, the value here says, let's see, calculate the value of K. So what I need to do, I'm going to pull RT over here. This is negative delta G over RT is equal to ln of K. Now remember what we did in our unit, our kinetics unit. If I want to undo the log, in this case, I raise both sides to that. Okay? So what I'm going to get is E to the negative delta G over RT is equal to K. Because if I take the natural log of the log, then I get K back. What I can do now is plug all this in here. E is negative 33.3. I'm going to leave out the units just to make this a little bit less crowded. Again, I've got to convert that to kilojoules, 0.00831 times T, which is 298, is equal to K. So K is equal to E to the 13.44, or K is equal to 6.9 times 10 to the minus 5. Notice that not only is our delta G negative, which shows that I have thermodynamic favorability, but K is big. And if K is big, that means when I go from reactants to products, remember, the larger the K, the more I am favored in that direction. And so a large K means that this reaction is thermodynamically favorable. So if a reaction has a very small K, the reaction is said to be reactant favored, and one should have a delta G value that is positive. So there's our relationship. On the other hand, if a reaction has a larger value of K, it is said to be product favored and should have a delta G that is negative. So that kind of shows you the relationship between delta G and K. Now, suppose that a certain chemical reaction has a large value of K and a negative value of delta G. Does this imply that the reaction rate is fast or slow? No. Thermodynamics tells us, and I like how he says this, the direction and extent, because that kind of the magnitude, we don't talk too much about the magnitude of delta G, but you can kind of look at, the magnitude kind of giving you an idea of the extent of a reaction, but nothing about the speed. All right, so let's look at another reaction. I've got copper sulfide going to its decomposing into its components of copper and sulfur. I'm going from one particle to three, solid, one particle to three particles. My delta G is positive, which means that it's not thermodynamically favored. So copper cannot be obtained directly from this. That's what it tells you. This is how useful this is. If I know this data, I can say copper can't come from this. We're not going to be able to do that easily, right? Because the reaction isn't thermodynamically favored. Okay? But what if I do two reactions concurrently, or I couple them? Remember we looked at reactions like this when we talked about Hess's law. So this is sort of similar. This reaction is not thermodynamically favored. This reaction is. If I couple the reactions together, I add them, then maybe I can get the reaction to occur. So what I'm going to do is I'm going to rewrite this equation here. Copper goes to copper. I'm going to put the states because they are important with these. Okay. Now, in order to use this reaction, I'm going to leave it as it is. I'm going to say sulfur plus O2 gas because it's on there, and SO2 gas. And I'm going to cross that out. I get copper sulfide plus O2 gas. This is a solid. Gives 2 copper solid plus SO2 gas. Right? Now, because I have coupled, or coupling means to bring together, I just bring these together. The delta G for the reaction is equal to 86.2 plus a negative 300.4 kilojoules. And that gives me now minus 214.2 kilojoules. And therefore, I have coupled the reactions. Notice that I didn't really do this like I do Hess's law. I didn't put the sulfur on the other side or do any of that. When I'm coupling, I'm just adding. I'm just adding them as written, and then I add these as written, and I get this now energetically favorable way to make copper if that is something that I want to make, let's say, commercially. Then I have a way to do that.